Welcome back to the next video, everybody. Today, we're going to briefly discuss the cup product as it relates to group cohomology. So the setup is we're going to let x1, x2, and x3 be G modules. So they are abelian groups acted on by a group G. And we're going to suppose we have a G module homomorphism phi from the tensor product of x1 with x2 to x3. Okay. Then the cup product will end up being a map from hi of gx1 cross hj of gx2, so hi of g this guy cross h2 of g this guy, to hi plus j of gx3, so hi plus j of g this guy. Okay, so you can see Milne's class field theory notes and a variety of different texts for the basic construction of the cup product. We're only going to define it in the needed case, which is the case I plus j is 2. We're going to do that here, and then hereafter we're just going to kind of use the cup product sparsely and by keeping in mind its properties. It's one of those things where in practice, you're using it according to its properties and not necessarily according to its nitty-gritty construction, kind of like the tensor product itself, for example. Okay, so the case I plus j equals 2, what is the cup product? Let's let F1 be an H2GX1. That means F1 is represented by a map F1 from G cross G to X1. Okay, let's let X2 be in X2G, which is H0 of GX2. So it's something in X2 fixed by G. We'll define F3 to be F1 cup X2, and that will be the two cocycle satisfying F3 of G1, G2. Remember, F3 should be a map from G cross G to X3, and we'll define it to just be phi of F1, G1, G2 tensor X2. Okay, so this totally makes sense. This definitely lives in H2 of GX3, and so the cup product is defined similarly for the pair H0 and H2, rather than H2 and H0. So I'll let you do that yourself. Okay, so how about for H1 and H1 paired together? Well, let's let phi k be an H1 of gxk for k equals 1, 2. So we're taking a phi1 in H1 gx1, and we're taking a phi2 in H1 gx2. We're going to define phi1 cup phi2 of G1, G2 to be big phi of phi1 of G1 tensor G1 phi2 of G2. Where this extra G1 here, which kind of throws the symmetry off, is because we need to make sure that the result is indeed a two cocycle, which you can check that it is. And so this cup product here is well defined. It is a map from H1 of GX1 cross H1 of GX2 to H2 of GX3. Okay, so let's look at an example of this in practice. So let's let P be a prime, and let's let A and B be in QP cross. Let's let phi be an H1 of GP Z mod 2Z be defined by phi of G is 0 if G root A is root A and phi of G is 1 otherwise. Then we'll define psi in H1 of GP mu2, where mu2 is the second roots of unity, by psi of G equals G root B over root B. Of course, you can identify mu2 with hom of the homomorphisms from Z mod 2Z to mu2. Okay. And so this gives a map from Z mod 2Z tensor mu2 to mu2. And mu2, of course, lives in QP bar cross. So then, okay, because we have a map from this tensor product, Z mod 2Z tensor mu2 to mu2, phi cup psi will be in H2 of GP QP bar cross, okay, by the theory we just discussed above. Now, if you fix a square root of B and let H of G be G root B to the phi of G, then you can show that phi cup psi times the co-boundary H of G1 times G1 H of G2 over H of G1 G2. So you have to check this is a co-boundary, and you also have to check that phi cup psi times this is the cocycle F corresponding to the Hilbert symbol AB sub P defined in a previous video. Okay. In fact, this cup product can actually be used to define the Hilbert symbol. So the Hilbert symbol can be defined in terms of cup products. Okay, so the upshot of all this is we have a non-degenerate pairing from H1 of GP Z mod 2Z cross H1 of GP mu2 to H2 of GP QP bar cross, which we know already, again by a previous video, is isomorphic to Q mod Z. And the non-degeneracy, by the way, follows from the fact and is in fact equivalent to the fact that the Hilbert symbol itself is a non-degenerate pairing.